Hello, everyone. Thank you for taking the time to join us today. My name is Kristen Vandewell, and I'm the Marketing Manager for Marmon Utility. I'll be your host for today's webinar titled Hendrix Polymer Distribution Insulators. This webinar will focus on the difference between porcelain and polymer insulators, the reasons polymer insulators are replacing their porcelain counterparts, and what benefits accrue from the change to polymer. Also covered will be the advantages of vice-top insulators over tie-top insulators, with the presentation of an economic analysis comparing the alternatives. For today's format, we'll begin with a 60-minute PowerPoint presentation, and we'll follow that with another 15 to 30 minutes of Q&A. Please use the Q&A tab located at the bottom of your screen to submit questions. I'll be screening them as they come in, and we'll relay some to our presenter during the presentation. Then, as time allows, we'll address all other questions during the Q&A segment. If you do submit a question and we don't have a chance to get to it, you'll receive a response in writing from our presenter. Now, I'd like to introduce you to today's presenter, Mr. Brian J. Treggor. Brian is a senior life member of the IEEE. He received his Bachelor of Science and Masters of Engineering degrees in Electric Power Engineering from Rensselaer Polytechnic Institute in New York, and a master's degree in Business Administration from the University of Pittsburgh. He's held various positions in engineering, consulting, and management at American Electric Power Company, Cooper Power Systems and Fisher Pierce, and most recently at Hendrix, where he is currently employed as Director of Technology and International. He has authored over 75 technical papers and articles for the IEEE and other national and international organizations. He has brought to fruition numerous high reliability power distribution projects in various sites on all 7 continents over a period spanning 44 years, with the past 28 years solely dedicated to aerial covered conductor systems. Now, I'd like to turn things over to you, Brian.
Thank you, Kristen, for that wonderful introduction. Hello and good afternoon to our webinar participants. Thanks for taking the time out of your busy schedule to join us and be with us today. For me, it's truly a pleasure and a privilege to be able to speak with you on today's very important topic, molded products and distribution polymer insulators. So without further ado, we'll just get right into the meat of the presentation. So we put together a presentation here that's a little bit different than the ones we've been doing. We're going to talk about insulator basics, which is something that we haven't done before. Then we'll get into the benefits of polyethylene insulators. Why are we using polyethylene here now in the US? Next, we're going to have to backtrack just a little bit and talk about dielectric incompatibility. Anytime we use insulators with covered conductor, they've got to be polyethylene insulators. We'll talk about why that is the case. Then we'll move into vice-top insulators, how vice-top insulators, differ from pin-type insulators. At that point, we'll move on to an economic evaluation. And we always say, talk to standards people and purchasing people and say, well, why am I going to buy a $6 or an $8, a $20 insulator when I can buy a $5 or a $6 insulator? So we'll get into the total cost of ownership, and that's really important. And then we're going to talk about what's new. We've got line post insulators, we've got tie top, we've got clamp type line posts, we've got wildlife covers. We'll talk a little bit about fire retardant insulators. Then we'll get into some really new stuff, trunnion style line posts, as well as station post insulators. So we're really going really far back here, but what is an insulator? Well, insulator is really a pretty darn poor conductor. It has 2 functions. It's supposed to be a mechanical support. You're basically going to support your electrical conductor and not let it touch the ground. So it's got a mechanical function, right? And then we've got the secondary function, electrical. We want to make sure that we're far enough away from the ground so we don't have a 60 hertz flashover. So we don't have a lightning flashover. So we don't have too much contamination to create tracking. So that's going to be a function of the mechanical design. How many sheds does it have? How high are the sheds? How big are the sheds? How wide are the sheds? So those kind of interesting things when we go into insulator design. So what does an insulator do? It essentially wants to maintain an air gap between that energized conductor and the ground. it's going to have mechanical stresses, everyday loads. You know, if it's a suspension insulator, it's got to be in tension. If it's a pin type or line post, it's got to be in compression. So it's got to resist mechanical stresses as well as resisting those electrical stresses. And sometimes those electric fields can get very intense. So we have the possibility of a flashover. So it must, in its proper design and application, resist those electrical stresses without flashing over. And then we've got the other stuff thrown in: heat, cold, UV, contamination. We've got to make sure that we protect against those things. We wanted to talk about a brief history of insulators. You know, really, how did we get to this point? Late 1700s, you know, they were putting up insulators they were very low DC voltage requirements from the telegraph industry. When we got around 1840, we started having different trials: wood insulators, cement insulators, and really wacky things like beeswax soaked rags to be insulators. And then we finally came upon porcelain and glass. When we got up to the 1890s, we started doing what was called wet process porcelain, and that was developed for high voltage applications because we started having higher voltages. Now that went all the way to 1960s, where we started the US trials of what we called ANSIs, or non-ceramic insulators. And those were essentially cycloaliphatic epoxy resin-based, and our European friends, you know, improved that with a fiberglass rod with various polymeric sheds. Cycloaliphatic epoxy resins had their time, but they phased out. They never really worked, and there's a history there we need not get into. Around 1970 or 69, Hendrix developed the first high-density polyethylene insulator, and ongoing improvements in material and design really revolutionized our industry. So these are really exciting things, and you can see through the next series of slides how that happened. For simplicity, we're going to talk about three different insulators. Distribution, 5 kV to 46 kV. 46 kV is really transmission in a lot of locations. Then we've got transmission, we'd say 69 to about 765 kV, 1000. 69 kV is usually sub-transmission, substation to substation, but it is transmission. And then substation insulators, and for all voltages, whether it's low voltage, high voltage, or what have you. We take a look at distribution lines, which is going to be the primary focus of our discussions here today. On the far left, you see the pin type insulators, mainly porcelain, growing use of polymeric, and very limited use of glass here in the US. The second one there, we've got our line post insulators, and they have been mostly porcelain, even though polymeric is coming in. The third one, we've got dead end insulators, usually polymeric, porcelain, or glass. And lastly, what would be our low voltage insulators, our spool insulators, the ANSI 53 class. We get to transmission, we're using suspension insulators. The new installations are usually mainly using non-ceramic insulators. Porcelain and glass now used less frequently, and we'll see why. See in the lower part there, line post insulators, mainly NCIs for new lines and installations, but still getting in some porcelain. And substations, we've got post insulators, the primarily porcelain, suspension insulators, primarily ceramic, and the cap and pin insulators, what we call our legacy type. So that brings us past the introduction and into the comparisons. How can we compare ceramic and NCIs or non-ceramic insulators? When ceramic, it's going to be porcelain or toughened glass. It serves us well. We've got metal components fixed with cement. So that's a little bit weird there. And they're covered through ANSI C29.1 through 29.10. When we go to non-ceramic, they're typically fiberglass rod with a rubber sheath, which is going to be EPDM or silicone, and weather sheds. Then we've got what we are offering, what we're talking about here today, high density polyethylene. And then the third there is cycloaliphatic epoxy resins. That's mostly not working these days. The metal components with our NCIs, the metal components are normally crimped. They're not cemented on there. So that's a real benefit there. And covered by ANSI C2911 through 19. Other comparisons. So when we use a ceramic, whether it's materials are naturally resistant to UV, they're pretty good with contamination, and they do pretty good with the electric fields. The materials are strong in compression, but weaker in tension. They have a high modulus of elasticity. They're very stiff. They're brittle. They require more careful handling. If you've gotten them bouncing around in the back of the truck, are you going to get chips and cracks, maybe breaking? They're heavier than NCIs, in many cases 2, 3, 4x the weight. Ceramic and glass in general has poor hydrophobicity, which means the surface can trap contaminants, and those contaminants later on can lead to cracking and failures. You look over on the right, and we're talking about non-ceramic. As soon as we go to non-ceramic, polymeric, we're vastly improving the hydrophobicity of those materials, which is going to be surface smoothness. So it's going to have a better contamination performance. Non-ceramics are strong in tension, weaker in compression, not a big deal. Deflection under load can be an issue, and it would only be an issue if I was building a 100 kV insulator, and it was very tall. Then I have a concern for cantilever. Where we're going with these things, that is not a concern. It's just an attribute. They're lighter. Non-ceramic is lighter. Again, could be 25–30% of the porcelain, and that's what you got there. So, $65,000 question. So why high-density polyethylene insulators? Where are we going with this? I'm going to take a step back just for a moment and talk about how we got here. Hendrix has been around since 1951. We're basically an overhead covered conductor company. We're doing spacer cable and tree wire, but we needed the polymeric insulators because you can't use covered conductor with porcelain. So we've been around since 51. We've got 5 to 115 kV covered conductor. We're working our way up to 138, 145 as we speak. We have installations on all 7 continents and well over 75 countries. We've got continuous development, design, safety, economics, reliability, and we're constantly improving our products and our offerings. Then, as part of our company, we have what we call our molded products division. We've been doing this since 1965. We built a new facility because we got too big. We built a new facility in 2012. It's 54,000 square feet. And we've been manufacturing high top insulators in ANSI 50 class 55 for over 50 years and vice top insulators for over 40 years. And we introduced line post insulators in 2012. So we've got 11, 12 years with those line post. And you see on the bottom, you've got a tie top pin, vice top pin, line post, and what we call porcelain, our primary option. So why do you want to buy Hendrix molded products? Well, they're guaranteed for life, okay? Hendrix will replace any insulator that fails, regardless of the installation date, regardless of the mode, whatever happened. We don't even need to know, we'll just replace it. We've got a 50-year track record of durability and reliability. We've got superior performance in any climate. We've got well over 30 million of these installed. They're manufactured, they're stocked in the USA, which means we've got short lead times. And we're not only that, we're supported and stocked at your local distributor. We've got channels nationwide, and we've got a US factory. Please come and visit us. We are very proud.
Brian, one quick question that came in is, What is the reason that porcelain insulators can't be used with covered conductors?
Lovely. You'll have that slide in about 60 seconds. Okay, we're world-class customer service and we're RUS approved, ISO certified, and independent lab test certified. We get our stuff tested at internationally renowned, internationally recognized test labs. So you get a independent test report. What else? How about our technical and functionality benefits? So with polymer insulators, you get a higher puncture strength. If we talk about an ANSI 55.4, the 15 kV class, it's going to have a puncture strength of say 95 or kV or something, 110 kV. We're giving you 220, 230 kV puncture strength. We've got a longer leakage distance. We've got higher impulse strength, massively better hydrophobicity. It's UV inhibited, it's got a greater track resistance, and it's got a long life. And the functionality is that, this is going to accept any conductor, it's going to accept any tie. This polymeric insulator can be used with bare conductor, it can be used with covered conductor. It's vandal resistant and it's directly interchangeable with porcelain, whether you've got a 1-inch pin or a 1 3/8 inch pin. Attributes, again, I'm going to belabor this. With lighter weight, I mean really lighter weight. It's compatible with all the conductors. We've got up to 35 kV. We've got C, F, and J necks, and there's the product line across the bottom. It's ballistics proof. We had these years ago returned to the factory, all shot up from hunting areas, and I won't say where they got returned from. So what we did is we went out to, I think it was the first time we went out with the Michigan State Police, and we asked them to shoot up a whole bunch of insulators. And since then, we've done that with other people that know what they're doing with firearms. So you can see, it's shot up with a 308 12-gauge buckshot. Even when the insulators are shot up, they continue to function, and they can we've even tested them to ANSI requirements. Some of them have even tested out after being full of bullets, which is kind of crazy, but it is a Benny. For people that know anything about vandalism, vandals like to see things explode. They shoot at the insulator a couple of times, nothing happens. They're probably going to go home or find something else to do, hopefully. So the challenges utilities face. So this is kind of an interesting slide. So much has happened in the last couple of years. We used to think years ago that products had a useful service life of say 40 years. So every year you had to replace 2.5% of your system. So distribution systems continue to age and need refurbishment with an increasing power demand. So not only have we the last 2 or 3 years not been replacing anything, so we're 2, 5, 7.5% behind, but we've got increasing power demand. We've got increasing load. We're really behind the 8 ball with building a viable, reliable distribution system. Then we've got, between the pandemic, we've got supply chain disruptions due to the almost non-existent production of porcelain insulators in the US. So people had to go overseas to get them, and they weren't coming in. It started accepting manufacturers that they weren't familiar with. So you see the bottom slide is the quality and consistent supply concerns remain with the overseas insulators manufacturers. So they're going out for help and really not getting it. The other realities is that when you buy bad porcelain, the deterioration due to impurities or voids cause cracks in the shell and the pin resin, leading to failures. With a standard pin type insulator, as you see in number 2 here, the lineman has continuous training on how to install all the different top ties to eliminate motion and abrasion. In number 3, you see flashovers due to dielectric incompatibility using covered conductor on porcelain insulator. I would address that in one moment. And then the end of the day, number 4 there, insulator failure can cause explosion and fires. So that's, pole top fires, explosions, and stuff we want to avoid. So there's the question, and I'm glad I included these slides in here. Why the need for polymer insulators when using covered conductor? So there's a term, it's called dielectric incompatibility. You're using two dielectrically incompatible materials in series. So if I looked at that covered conductor sitting on an insulator, I have a line voltage here. It could be 13.8 divided by the square root of 3. And then down at the bottom of that insulator, you've got a pin, you've got voltage. So to get from the top of the pin to the conductor to the pin, you essentially have a voltage divider circuit. So if I had a voltage divider circuit and it was resistive, I know that, if 20% of the resistance was across the cable jacket, it would carry 20% of the voltage drop and 80% across the insulator. However, this voltage divider circuit is a capacitive voltage divider circuit, which means that voltage drop is in inverse proportion to the capacitance, which means if you take a look at the insulator here, I've got a dielectric constant of about 2.3 for the high density polyethylene, whereas I have a dielectric constant of between 8 and 9 for the insulator, which means I'm going to force about 80–90% of the voltage drop across the covered conductor jacket, and only 10–20% of the voltage drop across the insulator. I've basically wiped out the insulators. There's not even there. All of the voltage drop is across the covered conductor jacket. Number one. Number two, there's a massive power factor change between the high density polyethylene and the porcelain. So it's out of phase. So I've got a high frequency partial discharge that's just hammering back and forth for the life of that system. So it's going to cause cracking and erosion. I'm going to get holes in my covered conductor with that partial discharge shooting out constantly. I'm going to eventually get microscopic holes in that covered conductor jacket. As time goes on, those microscopic holes in that jacket are going to become tunnels, if you will. And over time, with that partial discharge, it's going to start spitting out aluminum in the form of plasma. It's going to go right out that hole, boom, nowhere. So at some point you have 7 strands. A couple of years later, you got 6 strands. A couple of years later, you got 5 strands. A couple of years later, you got 4 strands. Next thing you know, it's the first day of May in Connecticut or Massachusetts or something like that. Everybody turns on their air conditioner and that conductor just anneals. It melts because it doesn't have the ampacity. You started out with a 7-strand conductor. You ended up with a 3 or 4-strand conductor. You have destroyed the conductor by putting that covered conductor on a porcelain insulator. This is historic. We've understood it. We have technical papers on it. You can talk to utilities that have had these issues, and it's going to lead to a failure. And you can see here they got covered conductor on a porcelain insulator, and at some point it just blew. It just flashed over the ground. And what I always say is damaged cable leading to failure is not a matter of if. It's simply a matter of when. The day you input covered conductor on a porcelain insulator, the first second you energize it is the first second you begin to damage your covered conductor. Now you can say, well, I've had covered conductor on 15 kV insulators, and I've had it for years and I've never had a problem. And I always say, wait, you will have a problem. My biggest issue with this is not only failures and reliability issues, but as that porcelain insulator erodes my jacket, what I'm doing is increasing this charging current on the surface of that, or the leakage current that's available. Should that conductor fall down, or should a lineman touch it, they could get electrocuted. Should a citizen touch that, they can get electrocuted. It's a safety issue. If you engage in design practices like this, you're hurting your conductor and you're creating a safety issue for your clients and your linemen. And yes, whoever asked that question, I'd be happy to answer that again, more online or offline, send you technical data, what have you, and we can continue that discussion. Here's more of the challenges we've been facing the last couple of years. So we've got costly unplanned outages due to insulator failures. Maybe we've got wildfires due to flashovers. Maybe we've got failures due to people shooting up the insulators. Maybe we've got worker time off due to injuries caused by heavy insulators. So here, you see a lineman, he's crawling, 4 feet or 5 feet out on a 8-10 foot cross arm. He's holding a 20-pound, 30-pound porcelain line post. It's okay if you do that once, but if you're doing that all day, every day, you got back issues, and those back issues are showing up in workers' comp issues. We've got insulators. Sometimes they need live line washing to eliminate the salt or the magnesium. We got products wasted due to breakage in the warehouse, banging around on the truck, chipping, cracking, all that stuff. We're maintaining inventory of different insulators, different ties. And at the end of the day, we've got angry people if the power's off. So how about, if you never run out of insulators when you need them, if you can completely reduce installation error by eliminating the use of a tie top, okay? So we're pointing to the tie top here, and that's probably the rest of the presentation mostly. And how about if you could reduce installation time by more than a half? And how about if you just eliminate body injuries by reducing the weight of the insulators by more than 50%? That's a massive benefit for our line workers. I'm going to touch on this briefly and then get back to it later. TCO, total cost of operation. So hidden costs hurt the bottom line. So let's take a look at we've got a porcelain insulator. We're going to build a 15 kV circuit with 20 poles. I guess we're not taking the dead ends into account here, but 15 kV circuits with 20 tangent poles. I've got my cost of my insulator. That's about $8 a piece, 480. Well, I got my ties. They're $550 each. So that cost me $330. I got my arm bracket and my armor rods, maybe about $21 each. I've got my truck and crew. We're saying that's about $300 an hour. Setup time, cost per pole, framing time, about 9 minutes per. Tie top installation time is 4 minutes. If you can do the tie top in 4 minutes, you can a heck of a lot better than I am. Installation up and down, 3 trips, that costs money to keep going back to that pole 3 times. And then we're saying up to 20% hidden costs. We got inventory management, safety stock, unplanned purchases, scrap, damaged material, delays, et cetera, et cetera. So it says the total cost of ownership is about 33 grand. So we'll take a look at that again in a little bit. But again, when we see an insulator, we say, well, it's $8 versus 10 versus 12 versus, that's almost nothing. The total cost of ownership is really important, not just the first cost. Again, so we're saying a better approach is insulators that exceed ANSI standards by as much as 30%. They're designed for faster and safer installation of more leakage distance, 30% higher flashover and impulse strength values, 30 to 40, 50% lighter weight, better hydrophobicity, vandal resistant. They won't chip or crack. They're environmentally friendly, completely 100% recyclable, and you're going to reduce inventory. And hence the Hendrix spice top insulator. So since 1965, Hendrix has been the innovator of high-density polyethylene distribution insulators. Our products have proven themselves repeatedly in the toughest conditions on this planet. And that's why they're the only distribution insulators guaranteed for life. Again, as we said before, they're manufactured and stocked in the US to perform in any climate. We've got over 30 million of them installed. We've got 50-year track record, and they're RUS approved, ISO certified, independent lab tested. So let's take a look at this insulator. You got to wrap your head around this. You know, this insulator has a tie versus a tie top. What is the difference? We've got an integral clamp on the top there that's going to hold your conductor either in the top position or in the side position. And if you look closely where the conductor is going to go, you're going to see we have inserts there. So we're going to use an aluminum insert for bare conductors. We're going to use a nylon insert for covered or bare conductors, but we have a composite insert that is going to replace everything. We're going to use a composite insert for bare, aluminum, copper, or covered conductors. It's easier for line work. It's hot stick compatible, massive time savings. Here's our facility. It says our Hendrix Amherst manufacturing facility is the most automated high-density polyethylene insulator facility in the country. I would say it's the most automated, modern facility on this planet. There's no doubt in my mind. And we hope you come and visit us. A couple of innovations that we've had with these insulators are shown on this slide. So we can use the vice top with covered conductor and plastic nylon, and you can use the vice top with bare wire, either with aluminum or composites. So again, they're easier for live line work, whether you're using bare or covered conductor. They're electrically compatible with all conductor types. There's no need for ties. We've got inserts designed for any kind of conductor. And when you install this, what you do is you tighten the ring until it breaks. So it's impossible to make a mistake on the tightening tension. As soon as you get to the proper torque, that ring breaks off. Okay, fantastic. Can't make a mistake. We got ourselves into fire retardant insulators several years ago with the obvious needs of this nation and our neighbors as well that have wildfires. So how we do that? When we introduce raw materials and when we introduce additives to those raw materials, we have to do type tests intended to compare the materials. So the in-house type test, we used our own in-house type test to simulate real-life condition using insulators rather than plaques made from raw material. So the insulators are subject to a utility torch, which in this case is a benzomatic MAP Pro flame, directly applied to that fin for 30 seconds. The flame self-extinguished in less than 5 seconds after the flame removed, and then melted drops from the insulator self-extinguished and didn't ignite cotton balls to below. So the universal standard for flammability test is called UL94V0. So that tests on plaques. With a plaque is like looks like a small deck of cards, if you will, or baseball cards or whatever. So UL940VO uses 10 seconds on the plaque, and then it takes it off, and they expect the flame to go out, and any drops should be extinguished before they hit cotton balls 2 feet below. Okay, so that says, yeah, now I'm fire retardant. But we don't use that test. We used, instead of a plaque, we used a full insulator. And instead of 10 seconds, we used 30 seconds. So we really fired that thing up. We really got it going. We really got it on fire and passed the test with vastly exceeded requirements. So very happy about that. We use a proprietary blend. Okay, this is another subject. This is not fire retardant. This is high temp rated insulators. So this is something that we got into, I want to say maybe 10 years ago. It took a while to get it out. So high temp insulators are capable of operating up to 200 C, 200 degrees centigrade. That's pretty darn hot. So, you know, continuous conductor temperature when factored with the amount of mechanical load applied. You know, we don't want these to actually deform the insulator. So you got to look at the catalog. I don't think that is an issue, but we put that in there as a caveat. So high temp insulators. Who's using high temp insulators? Why do people want high temp insulators? I imagine some of our engineers out there a bit thinking the same thing. What the heck am I going to use these for? So application for high temp insulators, basically we got legacy power lines currently being loaded beyond National Electric Safety Code recommendation. So some utilities are going to rate their lines are, you know, maybe for 140, 150 C in the summer, even though when you crank that conductor up to, you know, 140, 150 C, you've got so much of a sag that you possibly don't meet National Electric Safety Code requirements for clearance to ground anymore. So these are, again, they're legacy power lines. They might have a 1-aught, you know, ACSR where they're loading it. It was designed for 100 amps. They're loading it to 250, 300 amps, and that thing is sagging. It's time to change it out, but they haven't gotten to it. So it's basically for legacy power lines, and it's working. We're selling a bunch of these, so that's pretty happy. So I said I was going to get back to this total cost of operation. So now let's bring that porcelain insulator back and compare that to a Hendrix vice top. Same exact comparison. So we go up on the top. We've got 15 kV circuit, 20 poles, 60 insulators. First cost, porcelain cost $8. We're saying high density polyethylene cost 24. Holy, yeah, that's a lot. So that's 3 to 1. We're 3 times the cost. We've got ties, 60 ties at $5.50 each. Well, obviously they go for the porcelain, not for the vice top. You got armor rods and brackets. So those are the costs for those. We're not using armor rods for vice top, obviously. Then we've got our truck and through set of time framing, tie top installation up and down. And those are the numbers there for 3 trips up and down. And then we've got the total cost of ownership with the wastage, you know, whether it's inventory management, inventory safety stock, unplanned purchases, scrap, busted insulators, whatever. And we've estimated that at about 20%. So you see the total cost of ownership, even though you're paying 3x for that vice top insulator, you're saving, you know, $13,000, 60% savings. I mean, that's a massive savings. And you could look at that and say, no, that's not what I pay. I pay less than that. I pay more than that. I don't use armor rods. I don't have wastage. I don't have, you know, my inventory management is absolutely perfect. Still and all, you need to look, or you need to consider the total cost of ownership. Because the total cost of ownership is a lot like this iceberg we have here. What you see on top is, you know, the first cost. What does it cost to buy that thing? But really, a lot of the costs are hidden underneath that you really don't see. So this vice top calculator, which our Hendrix people can work through with you at your utility with your numbers, is basically a plug and play format. It allows comparisons using current costing, using your costing. You can change your labor rates. If the truck and crew doesn't cost $300 an hour, put what it costs, $600, $80, whatever. Your labor saving, your cost of porcelain insulator, your cost of vice tops, your cost of ties, the armor rods, and the number of trips up and down. And the hidden costs, If you think the hidden costs are more, jack it up 10, 20, 30%. If you think they're less, wipe them out. You're still going to have a savings, because even if you said, well, I've never broken an insulator, inventory management is perfect, you know, we only have one type, we don't have, even if you knocked out that $5,500, you'd still have a massive savings, okay? Because of all the other benefits in installation. Yeah, so we've got many, we've said probably hundreds of testimonials, but these, just a couple. The Snohomish PUD in Washington said one of the main reasons for switching from porcelain was the cost savings related to installation. The crews would not have to handle the porcelain pin insulators. Would not have to hand tie the porcelain pin insulators. Okay, the city of St. George, Utah says high density polyethylene is lightweight. One person can easily install the insulator. That's less costly, takes less time, and there's much lower risk of back injury for our workers. New Hampshire Co-op, which is one of our local utilities, says it's so easy to get the Hendrix products. They're made in the USA right here in New Hampshire, so availability is never a problem. Here in the Northeast, we have to react quickly to harsh weather. And you can't really predict when you're going to need insulators. Hendrix makes it easy to get the supplies we need. So that's about it. We just wanted to touch on the rest of our family and what's happening in the future. We've got line post insulators, tie top. These are fantastic. We've had these out again for 11 years. They're half the weight of traditional porcelain. They exceed the ANSI and RUS requirements. They're available in C and F neck, 15, 25, 35, and 46 kV. They're increased reliability. They are RUS approved. And obviously you can have reduced loss due to breakage in warehouse, job site, transport, storms, and the weight is significant. We've got a clamp top line post. Single universal clamps going to fit conductors from 0.187 to 1.75 inches. Obviously, you've got reduced SKUs compared to the trunnion style. They're more durable than porcelain. They're designed for vertical and horizontal applications. And you guessed it, made in the USA. We've got wildlife covers, so these are exciting for the APLIC compliant clients. And I already talked about flammability. This is so exciting. I just had to throw this slide back in here, different slide, but anyway, this is really exciting. So fire retardant insulator is going to be a big part of US and Canada's future, I believe. New product coming soon is going to be the trunnion style line post 15 through 46 kV. And then we're coming with a station post, TR208 through TR218. So that's going to be exciting to add that to the family. And with that, I will hand it back to our moderator, Kristen Vandewell. Thank you very much.
Thank you, Brian, for that excellent presentation. Before we jump into the Q&A segment, I just wanted to remind everyone that if you would like to request a certificate of participation for this webinar, please email me at kvandewell@marmonutility.com. I will also put this in the chat so you can copy and paste. And additionally, there will be a brief 4-question survey that will appear in your browser when you exit the webinar, and we would greatly appreciate your participation. And now for the questions. So Brian, one of the attendees asked, I'm not familiar with puncture strength as a technical specification. Which standard defines puncture strength?
I would say that's probably ANSI C29. Off the top of my head, it would be difficult to say which portion of ANSI C29 addresses puncture strength. But when you buy an insulator, one of the major characteristics, you got wet flashover, dry flashover at 60 hertz. You've got BIL, positive, you BIL negative, and puncture strength. Puncture strength is very important. Puncture strength is a 60 hertz. The voltage I need to puncture that insulator, whether it's porcelain or poly or what have you. So, and the beauty is, and if you send me that question in writing, I can send, and give me your email, I can send you the line in ANSI C29 that answers that question. But as we talk about puncture strength, there you raise an issue that I failed to address before. If you puncture a Hendrix insulator, and we've done it in the lab, I mean, it's almost impossible. We've almost never seen it in the field. Obviously, we can do it in the lab. You know, a 15 kV insulators, we're probably puncturing around 220, 230 kV. We get a puncture, you get a puncture hole. When you puncture a porcelain insulator, you get a couple of thousand shards of glass flying out at everything on cars, buildings, it's absolute catastrophe. Been lots of lawsuits with porcelain insulators puncturing. So that's another thing that we're going to get away from when we go to a polyethylene pin type or polyethylene any type of insulator. Sorry, it took a little too long answering that question, but
no problem.
Thank you.
This next question is in regards to using covered conductor with porcelain insulators, and it is, what is your opinion of stripping the cable at the insulator position?
Yes, so that was a technique when we discovered this in the late 50s, early 60s, that you can't use covered conductor with porcelain insulators. Somebody came up with the bright idea, hey, let's just strip the conductor and put it down on that porcelain insulator. The problem you have then is that when we have a interface between covered conductor and bare wire, which is what you've done when you just stripped it, you need a lightning arrestor, because the surge is going to come down the line, sit at that interface, reflect, and keep going back and burn that conductor down. It's very common knowledge in the industry. So basically what you've done is, as soon as you strip that conductor, now you need an arrestor. So you're not really saving anything. And if you don't put the arrestor on, you're going to burn the darn thing down. And lastly, you know, buying covered conductor and stripping it, you just completely nullified the value of a covered system. You buy a covered conductor system and then you're installing bare wire. It's like again, I would say it's like putting a screen door on a submarine. It just doesn't work.
Thank you, Brian. This question kind of goes in tandem with the other. Will damage also occur from PE wire at 5 kV voltages as well?
Question, probably not. Yes, there will be dielectric incompatibility. Yes, there will be partial discharge. I think at 5 kV, you're probably, unless you've got a shockingly thin diameter wire, you are going to be below the corona inception level. So, you know, here I am saying you might be able to, it's probably okay. I don't think it's okay. I think it's probably okay. I wouldn't do it, but it's probably okay at 5 kV.
Thank you. Are FR insulators a separate product, or is that inherent in all of the PE insulators?
Very good question. No, it is not inherent. If you took a FR insulator out of the box and you'd say, man, this looks like all the other insulators. I don't know if we have a special marking, but it looks like a standard tie top. It looks like a standard vice top, but it has the FR additives and it's more expensive. We don't have FR additives in all of our insulators. Whether we'll be doing that in 20 years from now, I don't know, but we don't today.
Thank you. Next question is, can you speak to the failure mode of over-tightening vice top insulators on the pin? And they said, you know, a particular issue on pins mounted directly to the pole.
Yeah, so when you've got a polyethylene, you got a plastic insulator. it's not really a failure mode. So what we've had is that people screw them down on that pin, and when they get to the end of the threads, they just keep screwing and basically push the top off a little bit and create a hairline crack, which can later lead to tracking and problems. So basically, when we convert a utility to polymeric insulators, we give them training. We have FAQ sheets on how to install it, turn it so many turns, turn it back. You know, if you're at the end of the threads, don't keep cranking because you're going to break something. But if somebody wants to send me that question in an email, I will answer it in writing and give you exactly what you need, hopefully.
Thank you, and I will provide your email in the chat as well for anyone who wants that. Next question is, what QA efforts are made to verify no voids are within the insulator, and how can you field verify pinholes or other damages to the insulators?
Yeah, okay. So X-ray testing is what we call, it's not a type test, it's a production test. So all our insulators are X-ray tested. So how do we verify there are no voids? We take an X-ray. Voids show up as bubbles in the X-ray. So we know how to do that. How would I verify that there were or were not voids in an insulator taken down from service? Let's say you have a failure or whatever, and you say, man, what happened to this insulator? I wonder if the BIL or the 60 hertz withstand or the puncture value was jeopardized by voids in that insulator. So how I would verify that would be with a simple hacksaw, cutting them up and looking for voids internally. You know, if I was in the field, it might be a little easier to send it to us and have us put it inside the X-ray and take an X-ray of it. And of course, we'd invite you to be there with us.
Thank you, Brian. Next question is, what does the putty do in the pin insulator?
Yeah, okay. So at the top of the pin is going to be a tiny air void. So what we do is that mastic, it's a mastic that we put on the top of the pin. It eliminates the air and prevents any partial discharge that may otherwise occur in the top of that pin cavity. Since there's obviously a high electric field there, we don't want to have any contaminants on the top of that pin cavity cause partial discharge and jeopardize the insulation. So we just fill that up with the mastic.
Thank you. And I did want to clarify just one thing. We got some more specific information for that puncture testing. It's defined in C29.1, section 4.11. Next question is, has Hendrix done any testing with magnesium chloride over spray causing tracking on the poly insulators? Mag chloride being used for ice on interstate highways.
We have done contamination testing in our own laboratories. We would be very happy to host whoever wants to do contamination testing with magnesium chloride, as I know that they use in some of the highways, say in Alberta, or I don't know who's putting this question up there. But yeah, we would be happy to engage in testing with whoever that electric utility is, and that should be an intelligent, interesting test.
Thank you. Next question. In areas where armor rod is used for dampening purposes, do you still need to use it with the poly clamp top insulators or another sort of dampener? And does Hendrix make dampeners?
The answer would be no. I mean, you might want to use it on a tie top, but you don't need an armor rod on a vice top because there's enough clamping there that you are damping those vibrations, the aeolian vibrations, if you will.
Next question, how extreme of an angle can you use the top vice top portion on the poly insulator?
Good question. Your design criteria when you're using vice top insulators would not change from vice top, from pin type insulators, as far as bending that conductor around a pin type or bending it around the vice top would be zero difference. So if you're saying, well, I'm 0 to 10 degrees, I'm bending it around an insulator, 25 degrees, I'm bending it around 2 insulators, and 35 degrees, I'm dead ending. Whatever your criteria for bending, single insulator, double insulator, or dead ending would be precisely the same as you would with any other insulator, bare wire or covered wire. No change in standards.
Thank you. The next question, is there a specific clamp insert for bare wire, and is there a specific insert for tree wire? Is there one you can use on both?
So historically with bare wire, you just order the aluminum inserts, or they call metal. For covered conductor, you ask for nylon inserts. In this day and age, you just ask for a composite insert, it's C, and that you can use covered conductor and bare wire. So yeah, it's very simple. One insert, one insulator for bare wire and covered, no inserts, no concern.
Thank you. What are the most common modes of failure that customers experience, both installation and otherwise?
Yeah, I don't think we have a whole lot of common modes of failure. We're not having punctures. The puncture strength is so high. I guess flashovers, but they're not failing on flashover. I guess, if we get shot up horribly and it flashes over, that could be a failure, but that's not a real. Yeah, no, I don't have a lot to tell you about failures, unfortunately. As a matter of fact, the failure rate of this insulator is, we had a utility do it. I want to say it was Northeast Utilities, which is a utility that doesn't exist anymore. It's Eversource, but they did calculations maybe 20 years ago, and said it was astronomically close to zero.
And I think one other potential mode of failure might be lightning. Is that correct, Brian?
Yeah, I mean, yeah, if it flashes over, recloser operates, nothing's there, comes back on, you don't lose power.
All right,
Yes, I mean, you can have a catastrophic flashover, you can have 100 KA lightning strike, you can have a 200 KA lightning strike, it's going to flash over, burn down the pole, knock everything onto the street. Yeah, there's always cases of catastrophic failures from significant electrostatic discharges.
How easy are they to remove when broken?
Yeah, I don't know how they break. They don't really break. How easy are they to remove? You just screw them off. Perhaps, yes, perhaps there's a question I'm not
We can
getting.
follow up for additional information. If the insulator is mounted at approximately 30 degrees on a side mount bracket, should the side groove be used?
Good question. Show me a diagram or a picture of what you want to do, and I will give you a professional opinion, recommendation. I'm uncomfortable answering that question when I'm trying to figure out the configuration that we're talking about. Next. Hello?
Oh, my apologies. The next question, sorry for that, I got on mute by accident. Does Hendrix make a transformer bushing or any equipment bushings?
No, not yet, anyway.
Do you X-ray every insulator before shipping?
The X-ray procedure as part of our routine testing or production testing is a predetermined statistical sampling method. So are 100% of them X-rayed? No. Do we have are we X-raying them to a 99.9% confidence interval with the statistical sampling method that we're using? Yes. So as far as you're concerned, they're 100% X-ray tested.
Would poly insulators have an advantage against pole fires likely caused by salt contamination?
Yes. And here's how you have an advantage. The hydrophobicity of the polymeric insulator compared with the porcelain insulator means that when the salt contamination sits on the porcelain insulator, it just sits there and grows and grows and grows and builds up and exacerbates itself and eventually tracks to the pin and you get a pole fire. With the high density polyethylene insulator, what you have is a extremely better hydrophobicity. So the contamination is going to fall from the sky and sit on that insulating surface. And then when it rains, the rain, because of the hydrophobicity, and hydrophobicity, you may or may not know, is a measure of the angle of a water droplet that falls on that surface. If you have poor hydrophobicity, that water becomes what's called a thin film. It just flattens out. If you have a high hydrophobicity, when that water hits, that water turns into a droplet and like a round ball and just bombards that insulator surface with washing rain and washes it off rather than making it a film and baking it on. So there is a benefit of hydrophobicity and operation in contaminated environments with high density polyethylene as compared to porcelain.
Thank you. And I think this might be our last question that we have. Is there a power utility industry standard for fire retardant insulators, IEEE, ANSI, that specifically apply to insulators? There are other industry fire retardant standards for other products like cable. What standard should a standard engineer reference in their specifications?
That's a good question. And again, it's going to be it's not for insulators. It's UL 94 V0, and it's a standard for flammability. I forget the precise name, but if you look it up, UL 94 V0, you'll see what that standard is. That standard is not yet in ANSI C29. Will it get there? Will it get there? I don't know. At some point, it probably will. It is not there yet. If you wanted to put a standard in your spec, I would say use the Hendrix standard because we're the only ones that has our own type test or type test for FR insulators.
Thank you. We did have one last question come in. At what degree angle would you recommend moving the conductor from the vise to the side mount between the neck and finger?
Oh, I guess more than 7 degrees. Is that correct, Sonny?
Yes, he said he confirmed that is correct.
Yes, 7 degrees on each side. Yeah.
Thank you, sir. I had to talk to one of the engineering managers.
All right. Well, thank you again, Brian. That does conclude today's webinar, but we appreciate you taking the time and sharing your expertise with us, and we hope that everyone enjoys the remainder of their day.
Thank you very much. Bye-bye.
Thank you. Goodbye.